Owen Mason, and this is my Physics 4 lab, Circuits and Capacitors. Introduction. The purpose of this lab is to predict the behavior of circuits in series and in parallel, using multimeters to measure the values of convection current and potential differences in a circuit, and to examine the behaviors of ohm resistors and capacitors, and also the effect of resistors overall on circuits. Initial current. In this experiment, we will be utilizing the circuit setup shown on the right. It has two 1.5 volt batteries, two resistors, and two ammeters. In this, we will be predicting whether the current at both the ammeters are the same or different. My prediction was that they would be the same, and the circuit shows that they are the same. The current in each one is 0.02 amps, and if we reverse the ammeter, it also reads 0.02 amps. The first principle is Ohm's law. This is that current through a conductor between 2 points is directly proportional to the voltage through these points. This is voltage equals current times resistance. The next is capacitancy. This is charge over voltage. This is how much an item can store a charge. The two rules we will utilize is Node's rule and loop rule. Node's rule is that the total current flowing in is equal to the total current flowing out of a system. The loop rule is that the sum of all electrical differences around a loop is always. We will be replacing one of the ammeters with a voltage meter. The expected readings through the voltage meter would be -3 volts, and the capacitor would end up becoming 0. The actual readings were also this. This is because the voltage meter has such high resistance, it is practically infinite resistance, causing it to have no current through the rest of the circuit. Potential differences around the circuit. This breakdown shows the potential differences broken up into segments. The first potential difference, 3 volts, is from the batteries, this shows that 0.96 volts were lost from the first resistor, and then another 2.04 volts were lost from the second resistor. This shows that the total voltage in 3 volts is equal to the total voltage lost, which is -3 volts. This proves the loop rule. Potential differences around the circuit, and this illustrates again how the voltage equals 0 as it goes around the circuit. The same materials in the circuit, but in parallel. One of the ammeters is in parallel with the 100 ohm resistor. This changes the current in the ammeters because when the ammeter, which has very low resistance, is in parallel with the 100 ohm resistor, the current will take the path of least resistance, which is the ammeter, resulting in each ammeter to have 0.06 amps. RC current. In this setup, we have a 10 amp bulb, a 20 amp bulb, and a 9 volt battery, and a 200 capacitor. When charging the capacitor, the current keeps moving from the battery toward the capacitor until the capacitor is fully charged, and then the current stops. When discharging, the battery is removed and the current flows until the capacitor has lost all representations of the charging of a 10 amp bulb and a 20 amp bulb. This shows how, based on this, the charge time for the 10 amp bulb is 20 seconds, and the discharge time is almost the same at 20 seconds. And for the 20 amp bulb, these are almost doubled, though slightly less. But this shows that they're directly proportional to the amount of resistance. Constants. The setup for this is a 30 amp bulb, a 9 volt battery, and a 200 mF capacitor. Charged capacitor takes measurements for 20 seconds as the capacitor discharges. Next, we will form a linear graph to determine the graph. From the data as shown on the table on the left, this results in the graph shown in the middle. Based on this graph, we will determine that the time constant is 6 seconds. The expected value of this was also 6 seconds. We're doing this in real life. What if you're using an actual ammeter instead of a simulated one? Would the real one be different? The answer is it would affect it slightly. This was because actual ammeters do not actually have 0 resistance, and actual wires do not have 0 resistance, so some of the current would be blocked. What if you're doing this lab in real life and used a real battery to charge a real capacitor with no resistance in the circuit? Would this prediction happen in real life? Explain. In the ideal model, it is predicted that the charge would charge immediately. However, this does not happen in real life because resistance is not actually 0.